Although my title doesn't have coherent states, I promise you they will come. First of all, I'd like to thank, of course, the organizers. This is a very interesting... Excuse me? Oh. It's a very interesting meeting that brings together a lot of different communities, and that's always interesting. And it gave me the opportunity to meet some old friends, which is also a lot of fun. I also would like to apologize to all the speakers from tomorrow onwards. Although I had intended to come and stay for the full week, it later turned out that I have to go to Hong Kong. I have to be there on Friday, so I'm leaving tomorrow. So I apologize because I don't like doing that, leaving in the middle of a meeting. But so the work I'm going to talk about is joint with these different people, and the problem is this problem of phase retrieval. So phase retrieval is a problem that is very famous. I mean, it got a Nobel Prize in medicine at some point. It's a problem that we've had in crystallography for forever. Typically, what it means is that you want, for instance, you measure the absolute value of a function, like by position in probability distribution in space, or probability or a probability distribution in quantum mechanics in frequency, but you'd like the whole state. You might know extra information, so you might know, for instance, that you might know the absolute value of the Fourier transform, and know that the function is positive, and that's the thing that was used in crystallography. You might another situation is where you might know the Wigner distribution of a corresponding to a pure state in quantum mechanics, and you want the state. So most of these cases are complicated by the fact that your measurements are noisy, and you want to reconstruct. So many algorithms have been proposed, and in many circumstances work quite well. They're typically iterative. You start from what you know, from what you're given, the absolute value. You then go to the other domain, you impose the constraint, and you keep going until you hope you will get convergence. Many of these algorithms do not have convergence proofs, actually, which is which is a challenge for mathematicians, and so people work on it. So that's all very, very old. A new twist came on this as a result of recent work by mathematicians on what they call compressed sensing. In compressed sensing or compressive sensing, what you have is that the information, typically you what you know is that you typically have. The original setup of compressed sensing was that you had a vector in a very large space, and you knew noisy in typically measurements. So you knew this plus noise, and from this you wanted to recover X. And of course, I mean, in this kind of dimensional setting, that's impossible in general, I mean, because it's very underdetermined. But if you know ahead of time that X is very sparse, even if you don't know where the sparse entries are located, then it turns out that in a whole lot of different settings, you have not only can you reconstruct, but you have stable algorithms and so on. So this is compressed sensing, and often the very first algorithms that were proposed for this was to say, what I want to do is I want to find x so that this minus y is small, and I want to also impose that x is sparse, and that's often done by saying that its L1 norm has to be sparse, because its L1 norm, you see, when you have an inverse problems and you try to minimize this, if A, even if A is of the right dimension, but is not invertible or is badly invertible, then you may put here in an L2 norm squared in order to minimize this, and you say your estimate is the argmin of this. And what you're doing is you're then penalizing all the possible x's that might live in the space of very small eigenvalues of A, where inversion is very bad, and that would blow up your solution. So what you do by putting a penalty like that is you put a penalty on every component that, if it becomes too large, forces the thing down again, and that stabilizes it. If you put here an L1 norm, then you're replacing a constraint that looks like that by a constraint that looks like this. And so you pay much more for small entries than you would with an L2 norm. And the result is that that makes it sparse. Okay, so that is something that had been proposed by Candace and Donahoe, and has in the last 15 years, 12 years, been seen an enormous development in signal analysis and statistics, and then Candace extended this to the situation where you want to recover low-rank matrix. So instead of saying I want to recover vectors, he says, imagine that I have this large matrix of which I know few entries and way too few to try to hope to recover the matrix, but I also know the matrix is low rank, much lower rank than its 2 dimensions. And a typical problem in this is in this world is the so-called Netflix problem, where you know for a whole lot of people a few of the movies they really like, and you do assume that there are not a zillion different patterns of liking different movies, and you like to reconstruct from the entries you have and from the fact that you know it for many people some way of finding that pattern. And it has lots of commercial applications. I don't want to even start telling you about them because they're scary. But so what Candace proposed was a similar thing to this compressive sensing. Again, for the entries that you know, you try to find a matrix that has things that are close to the entries, the noisy entries that you're given. But then in order to force the sparsity, the rank, you impose that it has a small trace norm, because that is kind of the equivalent of this. And so Thomas Stromer realized that you could use this in order to retrieve states from their Wigner distributions. I mean, say, look, I have the Wigner distribution, maybe noisy. I can try to get psi back. Because, of course, when you do things like this, well, let me get back. So this gave a new way of approaching phase retrieval. And people have been trying to use this new way of building algorithms for phase retrieval ever since. Okay, phase retrieval. So phase retrieval for frames. So if you have an expansion into a basis, then of course you can reconstruct a vector. If you start taking information away, you just take absolute values of the coefficients, you can forget about reconstructing. So you will need to start from an overcomplete set. I mean, a set that is more redundant than a basis. And very often it is useful, if you can, to work with what's called a frame. That's to say, a family of vectors, so you see it here, a family of vectors, so that the sum of inner products of an arbitrary psi with those vectors gives you a way of controlling the norm. So from above and from below. So A is positive, B is finite, and this for all possible situations. Then, when you have that, you can actually do a stable reconstruction from the frame. There exist dual frame vectors that allow you to reconstruct. And the phase retrieval for frames is what if your data are not those inner products from which we know we can reconstruct, but absolute values. And indeed, here are my coherent states. We have that problem in coherent states do constitute frames if you take them sufficiently dense. So let me take here I take the canonical coherent states. We know in that case that if you look at P and Q very continuously, that you have in fact mapped your functions from L2 of R to the Bargmann space of entire functions, which are functions entire in P plus IQ with a Gaussian weight, and F can have growth. Typically it does have growth, must have growth, but constrained by the fact that the product of the two is still square integrable. And you can, from these inner products, I mean, here we have the standard reconstruction of the identity, resolution of the identity for coherent states. Since in this case we know that the function we're looking at is analytic, we know that it's completely determined by its absolute value. In fact, if you have a function of a controlled growth, which is the case here at infinity, then the function is completely determined by its zeros. So even just knowing where the zeros are of these, I mean, just knowing all the coherent states to which you're orthogonal will determine your function up to normalization and phase. But of course, that's extremely unstable, because all that has to do with analytic continuation, and it becomes very unstable. So what we want to do is think of reconstruct stably from absolute values of inner products with coherent states. So, and also we want to do discretely. Now, once you discretize, if you take the PQ in these Gaussian coherent states I looked earlier, if I take them on a lattice in phase space, and I make the lattice I've normalized everything here with, shoot, no I didn't. Okay, so I should have written in an, okay, so I should have written PQ, so I had written e to the IPX GX e to the minus a half x minus q squared up to normalization and the phase factor. Then what I should do is I should take m p naught and q naught, and if you take p naught q naught equals to 2 pi, and for instance, I could take the case 2 pi m n, where I translate by integers, and here I have 2 pi times integer mx, then you know that the FGMN completely determine F, but it's not stable. This is the von Neumann lattice, and it will not give you F in a stable way. The reason is that in this case, for this particular case, we have indeed that the sum over Mn of FGMN squared is indeed bounded Bf squared, but there is no lower bound. So this, I cannot guarantee this. There is no A bigger than 0 such that this holds. But if I choose to go more densely, for instance, if I choose half the density at here, half the von Neumann lattice, a quarter actually in this case, But as soon as I go a little over the von Neumann density, I can reconstruct stably from the coefficients. But what for the absolute values of the coefficients? Well, actually I have a conjecture which I cannot prove. That is, as soon as you go at a density that is slightly better than half the density that I've indicated here. So the von Neumann density, but a little less than half in momentum and half so a little more than 4 points per old lattice cell of the von Neumann, then I believe you can reconstruct densely. I'll tell you why I believe that, but I'll... Okay, so I've come already to the idea of doing phase retrieval for frames, but when we do coherent states, we look at infinite dimensional Hilbert space, we look at L2. A lot is known already, although there are still unsolved questions about phase retrieval for frames in finite dimensions. And let me review that a little bit. So the first set of results I'm going to talk about are in a paper that by Jameson Cahill, Pete Casaza, and myself, and which was my first venture into phase retrieval. I think it has just come out in Transactions of the EMS. And in this paper, I just was basically the hired gun for infinite dimensions. I mean, these were people who had a lot of experience with phase retrieval in finite dimensions, and they wanted to. And it actually was surprising that things are very, very different. Okay, so again, we have, this is what a frame is. What you want is recovery. I mean, if I want to recover f from the f phi n, it's obvious that I will never be able to recover a global phase from f. So if you work in a real Hilbert space, which in quantum mechanics we're not used to doing, but in these phase retrieval problems and in signal analysis it often is useful, you want to recover up to an overall sign. If you work in complex Hilbert space, up to factors e to the I alpha. So recover up to a global phase. The distance we are going to look at is the distance. Since I recover up to a global phase, I'm going to say, if I look at two functions, then I'm going to say that if I add a global phase here, it doesn't make a difference. So the distance is going to be the inf over alpha that have norm 1 of this. And we already saw that in John's talk. All that means is that I'm interested in the distance between the rays rather than in between the vectors. So what we want is this. So we have here, and I'll write it down because we'll see this notation over and over again. So we go a phi of f is this collection of in the index set, it might be n or z or a finite set. And in this community, they talk about a frame doing phase retrieval, meaning it just means that map is injective. But more in general, you want more than just injectivity. You want also stability. Okay, in finite dimensions, actually in infinite dimensions too, there is a very interesting property, namely that a collection, a frame, will do phase retrieval if and only if it has this funny complement property. So if you remove a set from the full index set, so splitting your frame into two collections, then you want to have that either the collection you singled out or its complement still spans the whole space. And that already is an indication that in infinite dimensions things are going to be very different, Because in finite dimensions, it might be the case that indeed, if you remove a few, the rest will still span. And if you remove so many that the rest doesn't span, you already span with what you removed. But in infinite dimensions, we cannot expect something like that, indeed. So here again is an open question. We know that if a frame does phase retrieval, it must have the complement property. But we actually don't know that there's equivalence. In a real vector space, yes. But in a complex Hilbert space, people believe it, but they can't prove it. So if you get bored with a talk, take the back of an envelope and start. Stable recovery. So what we would like is that if you control the difference between images, so if you have an F and a G which give you data that are very close, then you would like F and G to be close, and the distance in which we want to be close is this distance. So you'd like to have control of this type, and in fact you can prove that the upper bound is easy. The upper bound is just something that comes from the frame bound. It's the lower bound, as often the case, that is a problem. So in finite dimensions, it turns out that C1, if you're injective, then C1 is positive. So you're always stable. If you do phase retrieval, then you can do it stably. And the question was, how can we characterize those frames for which you can do it stably in infinite dimensions? I mean, we don't expect it always, but when can you? And the answer is that you cannot. Never. And the proof is actually really easy, so I'm sketching it here. So if you have a frame, then you have these inequalities. And there's a first result that's not hard to see. I mean, if I say it with my hands, no matter how big an initial collection I take, I can find some k further on so that it has a very small inner product with this everything in the first. And so once I have that k, I can go somewhere further so that the whole tail has very little inner product. And that's what I'm controlling here. I'm saying that if you give me an n and an epsilon, then I can find for that first thing a k that's far enough, and then a tail that's far enough, so that the sum of the things in the initial and in the tail give me less than epsilon. And the only slight non-triviality in the proof is that what you do is you take the span of that first space, and then it turns out that the projection of all the space, the frame vectors on that space will give you, the sum of the squares of those will give you something finite. And that follows from the fact that I'm taking a finite dimensional space. And so once you have found that sum is finite, there must be a k for which that projection is very small, and so that will be the k you want. And then for that k, since the tail, the whole sequence, the whole series converges, you also can define a tail that is small, and you're done. Now, once you have that, so I started with things here. I have one in the middle, and then I have this tail going off. What I do is I take a phi k lies in the middle here. So I take a psi that's orthogonal to all of those. So I take two vectors that have very little overlap, if you want, very little overlap that I control. And now I look at two combinations, the sum of these two and the difference of these two. And what happens is that because they have very little overlap, I mean, in the middle, since psi is orthogonal, the way they differ, these two vectors, is orthogonal to all those ends in the middle. They have the same things. So the only difference between A of f and A of g, with the A I had defined there, is by looking at the start and the tail. And that I can control. And it's very small. So I have two vectors that, even though, I mean, because you can look at their distance, and it's going to be because phi k and psi are just orthogonal, that distance between phi plus psi and phi minus psi is going to be the same all the time, because it's given by the norms. And nevertheless, the distance between the images becomes small. So there's absolutely, I mean, it just follows from frame properties. There's absolutely nothing you can do. So, however, what you can do, I mean, and this is a traditional thing. I mean, so this is a traditional thing where you have an ill-posed inverse problem. And if you have an ill-posed inverse problem, you stabilize it by saying you know a little bit more. So what you can do is you can say, okay, so let's imagine that in my Hilbert space H, I have a whole lot of approximation spaces. And for the theorem to hold, I only ask that the dimensions grow. But let's imagine, I mean, because this is much more customary, that I have these approximation spaces And what I will have is that if I restrict myself to these spaces, then my frame, since the projections onto that space still form a frame, will give me stability. So I will have that there are constants. I mean, so that A of PVF Vm minus A PVMG is bigger, so times some constant g of m is bounds below f minus the distance between f and g. This distance that I've given up there. And this gm will be finite and will grow to infinity as m goes to infinity. And then I can define a, here they are. I was looking for erasers. So if I then define a set BR as the set of all f in H, for which f minus the projection onto Vm of f is smaller than, and it turns out that if you define this times f times r times f, then you can hope to prove a theorem of how well you can recover for f and g in such a ball, in such a space. I mean, you put this additional constraint in. And you have such a theorem. However, when you then try to check in practice what g of m can look like, it turns out it's really, really, really awful. I mean, so the stability can deteriorate very badly. So, for instance, if one case in which you can look at recovery from samples, this is a result by Gaurav Thakur. If you have a function of which the Fourier transform is compactly supported, then we all know, and every electrical engineer learns in kindergarten, that you can recover that function from its samples. So f is determined by its samples at the integers. Just between parentheses, if you have noise, and typically you have to oversample slightly, because the reconstruction formula is f of x sum over n fn sine pi x minus n over pi x minus n. And if you don't have this, but you have some epsilon n here, and you only have bounds on the absolute values of the epsilon n, your series does not converge absolutely, because this does not converge absolutely, and so you have problems. And that's why in hi-fi, the sounds are always sampled at 44,000 hertz, 44 kilohertz, because you have to sample at the frequency limit is 20 kilohertz. 2 samples per period gives you 40, and you do an extra 10%. But that's a little parenthesis. Okay, so determined by the FNs, maybe with a little bit of oversampling. But what Gaurav showed is that if f is real, so a real valued band-limited function, and then f is determined, meaning these samples do phase retrieval by the f of the lambda n over 2 if lambda is less than 1. And he not only did he prove that, but he proved a very, very nice algorithm for the reconstruction. So we now take a lattice that is actually even, I mean, I'm taking the things not at n, which are the ones I need for standard retrieval, not at n over 2, or a little bit more, which are the ones I would need for Thakur's example, but I take the ones at n over 4. So I have a density that is significantly better, and I can do phase retrieval. I have stability. I have injectivity. If I take then the span of those functions, then I can find functions, and I can actually construct them explicitly, so that the distance is bigger than an exponential in M for the VMs. So I take functions. And in fact, the construction is completely explicit. It's here I give you graphs of the function for M equals 5. Again, it's a function. What I do is I build a bump that is, and I build its symmetric bump so that they're still band limited. And then I look at the sum of the 2 bumps and the difference of the 2 bumps. And since they have a very, very tiny overlap, they must overlap since they have compact support in Fourier space, but the overlap is so little, is exponentially small, that in fact I get these terrible bounds. And in fact, when Gaurav said, in fact, that when he had done numerical experiments for his reconstruction, he had seen typically that there was an instability there. I mean, yes, he could do it, but what he would find is that very often when he took something like that with a big gap in it, signs would be wrong on one side. And then when he worked harder and harder, all of a sudden they would flip. And from then on, it would be okay. So what he was seeing was that he would get things correct in each island, but the coherence between the 2 islands was so little that it caused instabilities. And that leads us to our next observation, because we find exactly the same when we work with coherent states. So if you try, because I told you there are people who have built algorithms, they're the old algorithms, they're newer algorithms, try to reconstruct from the absolute values of coefficients. You find it does work, even if we haven't a convergence proof. But funny things can happen. So if we work with coherent states, we know that, for instance, if you work with the Gaussian, you know it's an entire function. An entire function has zeros, often. I mean, so there will be places where the inner products are small. So if you look at, I've made here a sketch of if I have a reasonable signal, and I look at its inner products with coherent states. So I look at the F with GPQs, and I look at in phase space. Let me suppose I put a threshold, and I only give you the domain where things are above threshold. You will typically find, I mean, that there is some area, and there may be holes in that area. We call these now atoll domains, because we have these lagoons. Typically, when you have a situation like that, it turns out experimentally that you can reconstruct very well from the absolute values of these. Provided I have them all, or I have them on a discrete lattice, that's fine enough. And we can prove that. I mean, that's a recent paper. All these papers are on arXiv, so you can find them. But if you have a situation where you have islands like this, and that is very, very common in audio, for instance. I mean, certainly when I talk and I pause for a little bit, you will find that in time-frequency space, things will look like that. I talk, and so on. But you may also have, very easily, that you have islands. I mean, for instance, there could be several speakers, or even if I'm speaking, there might be places where I have much higher frequencies than others. I mean, the phonemes and then the fricatives. And so if there is sufficient space between these, we see exactly the same instability as Gaurav saw. Namely, you try to reconstruct, and you will do fairly well. You get coherence on these islands, but then between the islands, phase can be off. And then and that's not surprising, because your GPQs are very localized. And if there's a big area where nothing much is happening, then that means that essentially the information that's sitting here is decoupled from the information that's sitting there, because the only way you get information is via these inner products. And this will give you information here and that information there. And it's true, there's some interpenetration, but it's very, very bad, because these things decay very fast. So what we can prove now is that if you don't care about the relative phase between these things, and you say, well, but don't I care? Well, not always. We did experiments. I mean, it's well known that if you change the phase on an audio utterance, that we don't hear the difference. But we did experiments where we took things that had islands like that, and we changed relative phase on each of these, and you don't hear a difference either. So for reconstructing, for instance, audio signals, it doesn't matter what the relative phase is. You don't really want to reconstruct F. What you want to reconstruct is each of these islands accurately up to its phase, its little global phase. If you want to do that, then you can do that stably. So, in a sense, the way the theorem, the no-go theorem, told us that you can never do it stably, because you can construct things that are far, don't penetrate, and you can flip them around, and you won't ever feel that. But that gives you an indication of what you might be able to do. Namely, if you have packages that are nicely coherent, then you will be able to reconstruct them up to their individual phase. And as I said, with audio, the experiment shows that we are not sensitive to that relative phase of these different islands. Even though, I mean, in a situation like this, if this is time, there's no moment in time where I have nothing happening. I mean, there is a gap here in time frequency, there's a gap there in time frequency, there's no gap in time, yet we are not sensitive at least in experiments we did on that to that phase. There are other situations where you do X-ray diffraction, where you want, again, you can only measure absolute values, but you want to reconstruct the scene with different objects. I mean, you might be interested in finding the geometry of each object and not necessarily exactly the relative phase of, I mean, in some cases you are, but in some cases you might not. So again, that might be an application. So, well, as I said, we have theorems, and they're on arXiv, and you're welcome to go look them up. I mean, they have lots of lovely complex analysis and other things. We are wanting to extend them to other coherent states than the canonical coherent states, so no longer be dependent on analyticity. That will require different proofs. They're in progress. And as admonished by the organizers, I'm stopping 5 minutes early on my time. So, thank you.
So, questions or remarks?
So, if you take some net of coherent states, and so they are not forms a frame for arbitrary distance between the.
Yes.
But what is Zori's statement? What is this distance? What is the maximal or minimal distance for this?
To have a frame.
For the frame. Right?
Okay. If you use the canonical coherent states, so the ones with the Gaussian, then you have a frame as soon as your density exceeds that of the von Neumann lattice. So if you look at GMN, so you have a constant e to the 2 pi I m p naught x, so I put in q naught, and let me erase this. Okay, so then these are a frame if and only if P naught times Q naught is less than 1. That has been proved. If you take not the Gaussians, but I take a general function that and I do the same thing. So here M and N are in Z. Same thing here. And then these can only be a frame. So here G is an arbitrary function in L2. These can be a frame only if P naught Q naught is less than 1. Of course, I can always, for any P naught Q naught, find things so that these things still do not span the whole space, and then I cannot be a frame. But you can only have frames if you're sufficiently dense. But what I was looking at was not just frame, but also reconstructing from just the absolute values. And then my claim is, so I don't know, but my reason for doing that is that we know that in finite dimensions, so if your space is n-dimensional, and then you can have collections from which you can do phase retrieval only if you have at least 4n minus 5 vectors. And the minus 5, let's forget about. But you need 4 times as many in a complex situation. In the real situation, you need twice as many, which is exactly what Gaurav had. He was in a real space and he did twice as many. But so my conjecture is the FGMN determine F uniquely. So we have injectivity up to global phase. Only if P naught Q naught is less than a quarter. But I can't prove that.
So in physical units, it's smaller than Planck constant.
Yeah, this is exactly the Planck constant.
And it does not depend on choice of
It will depend. This is, when I say only if, that is for all G. If I take G a Gaussian, I conjecture that it's exactly. That when P naught Q naught is less than 1, that it's if and only if.
Is it something common with L1 metrics for if you treat coherent states as projectors in L1?
That I don't know. I doubt it, but I don't know.
But we use some metrics. Is L1 metrics?
No. The metric between F and G is this metric. There. And that's in L2. So it's in H. It's in the Hilbert space. I'm sitting in a Hilbert space, and it's in that Hilbert space.
But my question is, this is the same when we start to consider coherent states as projectors, rank 1. Then we can take L1 this matrix for that. We restrict L1 matrix in trace class operators matrix to projectors and obtain some matrix on projecting Hilbert space. How this matrix is related to this one? To the matrix?
Yes.
I think it's the same.
It's the same. Yes, that's the same. Yes.
The same.
Yes.
Thank you.
Can you apply this to do holography without interference?
That's the goal with the X-ray diffraction. I mean, you work with X-ray lasers that and you measure. I mean, it's looked like a holography, but for very high frequencies. That's the idea that we would look at. But it's you can't say it's without interference. I mean, you have. I mean, when you do holography, you work with measurements of the absolute value of intensity measurements.
Yeah, you do interference to get a phase.
Well, but that's the reconstruction procedure. I mean, the measurements you have are phaseless.
Yeah.
And then how you reconstruct, of course, you will need to look, I mean, you need to get the phase back. So you can't hope to get the phase back without introducing it somehow. So the reconstruction is a different matter. I mean, but for the moment we want to prove that it's even feasible, stably feasible.
I have a question about the two pictures.
So the left side, I can't help but thinking of those that are sitting on a triangle.
Yeah, well, they don't have to be on a triangle.
Right?
Yeah.
You could sit on a circle. You see why I'm saying this probably. You could think of them as n coherent states on a circle.
Like this.
So now, then if you fix the circle, you take more and more of those, then you go to that picture above, right?
Mm-hmm.
So what is the transition? Because it's not sharp, right?
No, well, what happens is that it really has to do with how much information you get on each from. I mean, so if there were a bridge here, even if they were, I mean, if this has to do with how big a cell, what the influence is of each coherent state in phase space. If they start bridging it, then you can bridge.
So this is, to make this quantitative, it's a matter of the size of the overlap, right?
Well, yeah. I mean, so when you make it quantitative, it depends on the decay of your reproducing kernel in phase space of your. So it will depend on the decay of GPQ as a function of P and Q, and.
But when do you decide you're in the picture with the atoll and you're still, or when you're still in the other picture?
You decide on how stable you want to be. That gives you epsilons. I mean, you and so on. It's all in the epsilon deltas. But yes, I mean, this is just a moral picture. But you in the proofs give you all those things.
Can I ask you about the quarter there? How
Yes.
do you understand that? I understand the one above that. The one is clear.
Yes.
Not there, but the quarter in your conjecture? How did you think of that the quarter?
Because if I work in finite dimensions, so in n dimensions, in order to have a set that does phase retrieval, I need 4 times as many vectors in a complex space and twice as many in a real space. I mean, that has been... I mean, it's not clear whether it's 4n minus 5 or 4. I mean, I don't care. It's the factor, the front factor that I care about. And here also, in this case, this is a real situation. And there you needed a factor 2. So for finite dimensions, we know we need 4 and 2. 4 complex, 2 real. In infinite dimensions, we don't know anything like that. In infinite dimensions, we have one example where we can prove for 2. And I would conjecture that it's the same factors 2 and 4, depending complex real, and that would give us this in that case. And I've tried to prove it and I have not succeeded.
There is time for a last question.
Maybe I have one. You presented notation for coherent states in one dimension, L2 of R. Does it work in any?
Yes.
Okay. So it was really fast.